Okay, let's start this morning's proceedings. So I hope everyone, yesterday was a long day. I hope everyone got some rest. We had lots of events from the morning to the very end. So our first speaker today is Inder Kaur. She's probably the participant who's traveled from the furthest, from Brazil. Yeah, nice to have you here. So she's going to talk about the Hodge conjecture for moduli spaces of stable sheaves or sheaves on over nodal curves.
Yeah, stable sheaves. So first of all, thank you for inviting me and giving me the opportunity to speak here. It's been really nice. I've really enjoyed the conference so far. I really love the campus. It's very beautiful, and I've had already some nice discussions. So thank you. And I will be talking about the Hodge conjecture for moduli spaces of stable sheaves over nodal curves. Now, if I understand correctly, there are quite a few PhD students in the audience. Maybe you could just do a show of hands to. Oh, that's quite a bit. Okay, so that's one of the reasons I will start by recalling some basic notions, which is probably very tedious for the experts, but it would hopefully be helpful for the PhD students. So let's begin by recalling. So a pure Hodge structure of weight n is a pair Hz, HPQ consisting of, so put my definitions in a box so that you know what is it that I'm defining, consisting of one, finitely generated free abelian group, a lattice, which is denoted HC, and decomposition of the complexification HC, which is just HC, and this decomposition is, you can write HC as so. I hope this is not too low. So it's P plus Q equal to N HPQ, where these summands have the property that HPQ is equal to HQP conjugate. Okay, this is also called Hodge symmetry. And condition 2 is actually equivalent to, so, and since there are PhD students in the audience, I'll be giving some exercises. And hopefully tomorrow they will tell me the solutions. So condition 2 is equivalent to giving a filtration of HC. So this is going to be 0, 1, N, with Fn being HC here being N plus minus B plus 1. Conjugate. Sorry. Okay. So these two conditions, sorry. Okay, so these two conditions are equivalent. This is a good exercise to check, but so I gave the definition of a pure Hodge structure because when you hear the word, maybe it seems like something very scary, I don't know. But it's really not, so it's quite natural. And so there are a few examples. So let Y be a compact scalar manifold, and we can just take Hc to be the nth cohomology of Y with respect to C. This is the singular cohomology, modulo torsion. Okay, and HPQ is just HQ of Y. So the qth cohomology of Y with respect to the holomorphic P differentials. Okay, so then you have a pure Hodge structure. Of weight n. Okay. Now the thing is that the thing that we will be most interested in, and that will keep coming up, and also I think it's very interesting for this audience, is that if you take X to be a smooth projective curve over C, so I'm actually always working over C. So it is always over C. Okay, so this admits, because this is a compact scalar manifold, this, by what I have said in one, gives you admits a pure Hodge structure, and so does the moduli space of stable vector bundles. So let's say this is co-prime over X. That also is compact scalar and admits a Hodge structure by this first example. So okay, now the thing I'm going to talk about is the Hodge conjecture. Okay. Now, as I said, I know that there are PhD students in the audience, and I don't want to assume that you're used to this, which is why I've given you the basic definitions. And so let Y be a smooth projective variety over C, and Y admits the Hodge decomposition. So we have that HRYC is equal to over I R minus I. Okay. Now, guessing most people are familiar with this, but so denote by ZPY the finitely generated the free abelian group of algebraic cycles. Cycles of Y. So, what is an algebraic cycle? So, Z and ZP Y is of the form Z can be written as N1 Z1 plus NK ZK NI in C and ZI irreducible variety of Y codimension P. Okay, so these are the algebraic cycles. And now the next ingredients we need in order to talk about the Hodge conjecture is that suppose we have V in Y a smooth subvariety. Okay, so there is a embedding, and we have okay, maybe I'll cheat here a bit. So this is the embedding. I embedding and V star H2P Y and the push forward. So it was a bit on the level of cohomology. Star 1. This is called the fundamental class of V. Okay, so you have a smooth subvariety, you have the embedding, and then I'm saying that you have this map on the cohomology, but as you see, I was trying to think a bit there, because I'm actually cheating here. There is no push forward on cohomology. So what I do first is that I go to homology, then push forward, then go, so first to Poincare duality, go to homology, then push forward, then do Poincare duality again, and go back to cohomology. Okay, so hopefully that's clear. Now, so the thing is, this is when I have a smooth subvariety, but I might have a singular one. And what do I do then? I do Hironaka, and then do the same thing. Okay, so the cycle class map C goes from CPY to H2P YC. Okay, and what this does is that it takes your V and sends it to its fundamental class. The fundamental class was defined as the push forward. Okay, so now this is called the cycle class map, because what you're doing is that you are taking an algebraic cycle, and the image here is called classes. So let me make a remark. So first of all, image of C is contained in, so this you need to show, it's not obvious, but you can show that the image of C is contained in H2P Y Z intersect HPP Y C. Okay, so the image of C is called algebraic classes. So there you have algebraic cycles, here you have algebraic classes, the image, and this here, H2P YZ intersect HPP YC, this is called Hodge classes. Okay. So this will be denoted by H star, H star alg y, and this will be denoted H star Hodge y. Okay. So so what this statement is saying is that the algebraic classes are contained in the Hodge classes, right? And then the question is every Hodge class coming from an algebraic class? Okay, so we know, I mean, we don't, you need to show this, but we know that H star alg y is in H star Hodge y. Okay, but question, and this is the, sorry, I should really say integral Hodge conjecture. Hodge conjecture. Which is, I will just abbreviate by IHC. So the integral Hodge conjecture asks, is this an isomorphism? So I don't know, let's just call this phi. No, sorry, it already has a nice, yeah. Okay, so is this surjective? Okay, so is every Hodge class coming from an algebraic class? So this seems like, you know, some definitions and a statement, but really, why should this be plausible? So let me go back. So I know that there are PhD students, so here is an exercise. Whoa, sorry. Erase this. So the reason why Hodge thought that this might be plausible is because it is true for p equals 1. Okay? So I would like to see tomorrow lunchtime from the PhD students why it is true for p equals 1. It's a nice exercise to do. So exercise, show C true for p equals 1. Okay? And this has a nice name of its own. It's actually called Lefschetz 1, 1. Okay? And if you need a hint, it's going to be to use the exponential exact sequence. Okay, so it was plausible, hence it was conjectured. But then AHC is false in general. Okay? And there are counterexamples. By Thea Hisbrook. And I mean, this one is kind of trying to create a Hodge class which has torsion because you know that you are in Z, so it's more or less the idea you would have, although I mean, it requires quite a little work. But then there is another one which is not coming from torsion, which is by Kolar. I always get this one wrong. I don't know if it is this way or the other way. I always make this mistake, and there are sometimes, yeah, people really furious. Okay, so so this is the integral Hodge conjecture is false, but what we call the Hodge conjecture and this is, I think, as of until today, it's unknown to be true or false. I mean, it's known to be true for quite a lot of varieties, but there is no counterexample. And this is basically you. So there you had integral coefficients, and here you have rational. So you take your y q intersect HPP y c. Okay, so this is not known. So P is sorry, yes. Okay, yes. So this is not yet known. So what this is saying, so if you find this kind of abstract and you want to understand geometrically what these things mean, what you're saying is that does every Hodge, does every rational PP class necessarily come from a codimension piece of variety? Okay, so when you think of it this way, and you see it really when you do this exercise, that this is exactly what this is saying, then you see the geometric intuition behind this. Okay, so this is the Hodge conjecture. So I hope it is followable for the PhD students. Okay. Okay, so now the question is, there are quite a few examples in which the Hodge conjecture is known to be true. This conference is about moduli spaces. So I'm actually going to talk about the cases when it is true for moduli spaces. So some examples of, so I'm only going to give a couple, moduli spaces of sheaves. Where Hodge conjecture holds. Okay. So, what is the simplest moduli space that we can think of sheaves over a curve? So let's say we let X to be a smooth projective, and I'm going to keep a gap here, and I'll fill this up in a minute. Curve of genus G greater than or equal to 2. Okay. So then Hodge conjecture holds for 1, the simplest moduli space of sheaves that we can think of, which is the Jacobian. So rank 1, degree 0. And no, I'm coming to that. So the point is that, as Balaji is already trying to point out, is that, so first of all, how do you show that this is true for the Jacobian? So there is, as we know, that if we have, for P equals 1, the Hodge conjecture is true. Okay. So if we can show that our Hodge ring is generated in degree 1, then we are good. We just apply Lefschetz 1, and we have it. So this is a common technique that keeps getting used in most of these proofs for why the Hodge conjecture is true. Okay, so if you can show that it is generated in degree 1, you're done. So how do you show for the Jacobian that it is generated in degree 1? So the idea is that generated by 2. So this is P equals 1. Okay. And the idea is that you basically look into this moduli space of curves, and you see for the curves for which you can get this. And somewhere in the proof, which is very long, it's in Birkenhage-Lange. I do not know exactly who this was first due to. So But there is a proof in Birkenhagen-Lange. So what they do is that when they are looking at how you can generate this in degree 1, and this is done namely by the theta divisor. So this is the Jacobian is a principally polarized variety. And it has a theta divisor, the principal polarization, and you show that it generates that, and then this generates this. So one of the key things you need to do in the proof is that you need to throw away a lot of curves for which this doesn't hold. Okay, so you keep throwing away curves. So as Balaji was trying to say, this is not true for any smooth projective curve. Okay, you need the curve to be very general. But I hope now you understand why the assumption of very general comes in. So very general means that I look at a topological space and I remove countably many proper closed subsets, and the elements that remain, they're very general. Okay, so this is true for very general. And then if I look at the moduli space of stable vector bundles with fixed determinant of odd degree. No, sorry, let's first do 2. Okay. Then this, for this variety as well, the Hodge conjecture holds. Okay, and this is due to Professor Balaji, King, Newstead in rank 2, and in general rank, this is due to, cannot really say, but Biswas, Professor Biswas and Professor Narasimhan. Okay, so the thing is that before I launch into the question that we are trying to solve, I would like to give a very brief sketch of the proof of Balaji King Newstead. So it's very nice to have Professor Balaji here because now he can tell me whether I actually understand the proof correctly or not. So the couple of things that I do need before I can give the proof is, so I'm just going to state these as facts, is one, that by Mumford Newstead, there exists an isomorphism of pure Hodge structures. So I did not tell you what is a morphism of pure Hodge structures, but you can guess it's something that will take the lattice to the lattice and preserve the filtration, right? So pure Hodge structures going, let's call this phi, going from H1xz to H3 mx to Lz. Okay, and actually they, so the basis here goes to, which I will call gamma I. Okay, so I goes from 1 to 2g. And they actually use this, I'm not going to go too much into it, but they use this to then give a isomorphism between the first, between the Jacobian of the curve and the second intermediate Jacobian of the moduli space, and prove a kind of higher rank Torelli. So then, so this was around, I think, 69, and the Newstead showed circa, I think, 72, that there exists alpha in H2 see beta in H4 and gamma i's. The gamma i's are the ones that are the image of this of the basis and under this map in H3. Z such that alpha, beta, gamma generate the homology ring. Okay, so we have 2G plus 2 generators, and so this is what they show. And then Balaji King Newstead use cleverly this fact and the fact that we know already the Hodge conjecture for the Jacobian to show. So this is a very brief sketch. Balaji King Newstead. So what they show is that there exists surjective morphism going from H star alg x q alpha beta to H star alg and so, I mean, this morphism, they show that it exists without even the algebraic classes, but then you can show that it really takes algebraic classes to algebraic classes, okay? And then what you want to show is that, you know that the algebraic classes are inside, there is an injective morphism in the Hodge classes. But what you want to conclude is that this is an isomorphism, okay? So you want this to be an isomorphism. So this is, as I said, it's quite neat that what you do is that you have x, so you have it here, but actually it's not just injective, but because we already know that the Hodge conjecture holds for the Jacobian, this is also surjective, so it's an isomorphism. And then you use this to get and this diagram to get the isomorphism there. So this is the idea in a nutshell. Is that correct? Good. So, so yes, the question would be now, so yeah, I should point out that again in their proof, because they are using the proof from the Jacobian, the genericity condition has to be carried through. So again, they assume that the curve is very general. Okay, so the question is, what happens if x is irreducible nodal? So can we consider the moduli space of sheaves and redo Professor Balaji King Newstead's proof? So let's first define the setup. So x0 be an irreducible nodal curve with one node x0, L0 an invertible sheaf of odd degree, and denote by ux0 to L0 the moduli space of rank 2 stable torsion-free sheaves with fixed determinant L0. Okay, and here you should stop me and say, what do I mean by fixed determinant? I'm on something singular. So when I am considering something which is smooth and I'm just considering torsion-free sheaves, then I take the locally free resolution and I use that, the locally free sheaves there, I take their determinant and I use that to define the determinant of the sheaf. But I cannot do this if the underlying variety is singular, okay? Because the locally free resolution is no longer finite, okay? So what do I mean by fixed determinant? And this is a definition due to Nagaraj Seshadri. Where they define this thing as saying that what, so a sheaf F has determinant L0 if there exists a morphism from the wedge of the normal determinant that you would take to L0, okay? So normally when you have something which is singular, this can pick up torsion. So it wouldn't make sense to just define this. But what they say is that you say that it has determinant L0 if there exists a morphism, which is an isomorphism outside the node, okay? So this is what I mean by fixed determinant. So, okay. Now, even if I have the fixed determinant everything, the thing is that this variety is singular, okay? So the Hodge conjecture doesn't quite make sense as it stands. So what we prove and again we ask the genericity condition is that let x0 be a very general. So what I mean by a nodal curve being very general is that when I take the normalization, that is very general, okay? Very general nodal curve. Then Hodge conjecture holds for the singularization of ux0 to L0, okay? So then it makes sense, and I show that it holds for a desingularization. So what is this desingularization? Actually, I'm very happy that my talk was after Balaji's last talk, because Balaji cut down the preliminaries for me by quite a bit. So I was very happy. So this desingularization is actually something that Balaji talked about yesterday in his talk. So we embed x0 in a regular family of curves. Okay. This is the unit disk, such that all the other fibers, such that the central fiber is my nodal curve and all the other fibers are smooth. Okay. So I have this, and then as Balaji was saying yesterday, that there exists a relative Gieseker moduli space with some very nice properties. So So there exists a relative Gieseker moduli space. Okay, so which I will denote by G chi 2L. Okay, so it's the, I'm writing small, okay. Yeah. The whole thing is small? Sorry, I normally write quite small, so there exists a relative Gieseker moduli space G chi 2L. Yeah.
So this, for the fixed determinant case, the co-prime situation.
Right.
This construction is due to Takeshi Abe.
Ah.
And comes from the work of Michael Thaddeus' thesis.
Yes, that is, yes. So yes, thank you for pointing out, I should have said this. So yes, this was shown that this was a flat projective morphism.
This is like the fixed determinant case.
Yes, the fixed determinant case is in, and also I think Seattleston also worked on it.
In his thesis.
Yes,
there.
right. Right. I think it's just 1D. Thaddeus. Yeah. Okay. Maybe this is a bit small. Okay. So they show that there exists this relative Gieseker moduli space, which enjoys some very nice properties, as we saw yesterday. And one nice property, very nice property, is that for all the smooth curves, the moduli space is smooth. And I don't know if I should draw it like this. And for the central fiber, we have SNCD, simple normal crossings divisor. So this is smooth, other than for this part. So, and this has, in our case, because we are in rank 2, it has G0 and G1, which I will call 2 components, okay, which are smooth. So this has some very nice properties, and the rest of the fibers are, so let's say GXT to LT is just the same as your normal moduli space. So MX to L, for which we already know the Hodge conjecture, thanks to Balaji King Newstead. So,
If you don't mind.
yes.
So your base family is to an irreducible nodal curve?
Yes.
Okay. So I think this kind of degeneration,
Yes.
fixed determinant, at least from what I understand, you will get one of the components to be non-reduced.
Right.
And only one component is smooth.
Right.
So you'll have to do a further degeneration to something which is called a semi-stable curve. That is, you can't work just.
Yes. I was skipping that. I was putting it under the carpet because yesterday.
That it is smooth. I was just.
Yes, you're right. No, it's
one of them will be smooth, and the other one will be non-reduced.
Yes, you're right. You're absolutely right. So one of them, as you were saying as well yesterday, is is the desingularization of UX0 to L. Okay, so I just call this one G0. So that's no prime there. Okay, so as I said, the other fibers are smooth. So the basic idea is to somehow use already the proof of Balaji King Newstead that they have proven it in the smooth case to get this for this one GX G0. So this whole fiber is called 2L0, okay? The entire fiber. And the component that is the desingularization of ux0 to L, I'll call G0. Okay, so how do you do this? So so G0, so I'm taking the smooth component and I'm going to prove it for that. And as we saw yesterday, that there is going to be this is the desingularization of the moduli space of torsion-free sheaves. So, okay, so how am I doing for time, just to make sure I don't, 15? Oh, okay. Right. Okay, so, sorry, okay, the timer is there, thank you. Right. Okay, so I just have 15 minutes to give a very, very quick sketch. So I hope so far everything is clear. Did the mic go off? Right. Okay. So right. So how do we show that the Hodge conjecture? So now the problem reduces to showing the Hodge conjecture for G0. And the question is, how do we do that? So, right. So the goal is to prove the Hodge conjecture for G0. Okay. And the strategy is that we first show that the Hodge classes of every Hodge class of G0 comes as a restriction of the Hodge class of GH0. Okay, the entire fiber. And secondly, so this I will not prove because this is kind of computational and technical and you don't really see too much. The second idea is that every Hodge class of GX0 to L0, we need to show that this is algebraic. So here again, you should stop me if you know the theory, but if you don't, I understand that you don't see what are the problems. But the thing is that when I talk about GX0 to L0, this entire fiber, this is not smooth, right? So actually there is no pure Hodge structure on this. The Hodge structure on this is mixed. I say that every Hodge class of G0 comes as a restriction of a Hodge class of GX0. So GX0 is the whole fiber? Exactly. I'm going to define that. Thank you. So this is the point. So in the case when the variety was smooth, I had the pure Hodge structure, and I told you that you have this decomposition, and I defined the Hodge classes as being the image of this thing, and the fact that it lies in this H2P intersect HPP. But what do I mean really by Hodge classes in the case when something is singular? Because I have no pure Hodge structure. But thanks to the work of a lot of people, and I might forget somebody, but Griffiths, Schmidt, Steenbrink, Deline, we do have mixed Hodge structures on singular varieties. Am I forgetting somebody? Yes. Yes, exactly. Which is, thank you for pointing that out, because that is one of the things that we use in order to do the computations. We use the fact explicitly that this is normal crossings, because then we can use Steenbring spectral sequences, and things are very nice. And that's why I said that it was very nice that yesterday Professor Balaji really stressed this point. So yeah.
But you said that the U1 is non-reduced. So is this a problem or?
No,
You
can do the degeneration.
And then you use this.
Yeah.
You will have such a flat degeneration.
Right.
That is, the base curve is not nodal now. You like to think of some sort of a semi-stable curve.
Right.
Normalization with one single P1.
Yep.
And then you can use. You can as well work with this. Yeah.
Okay.
I was only correcting that statement that the base, if it's just irreducible, then you want.
Yes, I was trying to keep it a bit simple, but thank you for pointing that out. That's very important. Okay, so what do I mean by these things? So first of all, as I said, that we have for a singular variety, we have definition of mixed Hodge structures. So maybe I put the whole mixed Hodge structure thing here. So for a pure Hodge structure, we had a pair, and for a mixed Hodge structure, we actually have a triple. So Hodge structure. So this will be H, Z. Consists of one, an increasing weight filtration, so which is denoted W, and the dot is at the bottom. W1 on HQ. So last time we had the complexification tensoring with going over C. Here we have over the rationals. So this is C tensored with Q. Okay. So we have an increasing weight filtration and a decreasing filtration, again of the complexification. So HC being 0, so this is F0 containing F1, and as we had before, Fn. Okay, and so we have an increasing weight filtration and we have a decreasing filtration, and the second filtration, which is always with the dot on the top. I always mix these things up. This induces, so this filtration is such that it defines a pure Hodge structure of weight K on the graded piece this is the G R K up, sorry, W up, down. WK plus 1 HQ, where the WK is equal to, W top k is equal to W minus k. Okay, so this induces a pure Hodge structure on the quotients of this one. Okay, so this is how you define a mixed Hodge structure. So you take your lattice, and now instead of one filtration, you have two, and you have to be a little bit careful. But this normal filtration that you had before, this is now inducing pure Hodge structure, not on the whole thing, but actually on these quotients. Okay, so now the thing is, so we have a pure Hodge structure. We have a mixed Hodge structure in GX0, and so as we all want to know, what are the So what do I mean by a Hodge class of GX0? So Hodge class of GX0, so H2I Hodge, is kind of what you would, think you should do, which is to use the part which is smooth. So you just do the HII of the graded piece. Okay. Because there you have, so on the graded pieces, you have pure Hodge structures, right? So you just use that to define the Hodge class. Okay. Now the thing is, what I also wanted to say is that this, again, mixed Hodge structure sounds, a bit abstract maybe. So let's do a small example. So the thing is that if something is pure, you can always define a mixed Hodge structure on it. A very trivial mixed Hodge structure. So if something is smooth. So if something is smooth, then you can just take you have your normal filtration, and now you want your weight filtration to be just xq to be 0 for I less than n, and this parts to be just hn xq for I greater than or equal to n. Okay, so I hope this is clear so far. So now the thing is what I wanted to do.
Your W2I?
Yes.
Your W2I?
Yes.
That's an I.
Yeah. Yes, sorry, thank you. Okay, so is that okay? All right, so okay, so I want to go to the sketch of the proof very, very quickly. So what we need to do, so as you see, you can always put a trivial mixed Hodge structure on the smooth fibers. So your singular fiber has a mixed Hodge structure, and on the smooth ones, you can put a trivial one. Okay, so you will be able to get a specialization morphism. Maybe I write it like this. H2P GX0 2L0 Q to H2P GXT to LT. Okay. So I hope this is clear for here T not equal to 0. Okay. So you have your cohomology of this singular fiber and the cohomology of the general fibers, which are smooth. And there is a specialization morphism. But the thing is, and the reason you want to look at this is, as I said, we already know for the smooth case, right? So here, if we were to be able to have that algebraic classes go to algebraic classes, and we would have here that this is going to be an isomorphism by Balaji King Newstead. And we have a kernel. So, and then we know that this is going to be, so hang on, I just need to explain this. So the thing is, you would be able to forget about the alg for a minute. You will have a specialization morphism, okay? And you have a specialization morphism no matter what Hodge structure you have on these fibers. But the thing is, you don't have a morphism of mixed Hodge structures. You know, if you just take the singular one, I'll just take a couple more minutes. Okay, so if you just take the normal trivial mixed Hodge structure on the smooth fibers, you won't have that this morphism is a morphism of mixed Hodge structures. So there exists a mixed Hodge structure called the limit mixed Hodge structure, okay, such that, so if, as I said, you forget the alg for a minute, you have that this specialization morphism is really a morphism of mixed Hodge structures, okay? Now, in order to show this proof, what we need to do is show that we have the specialization morphism, but then we need to have that the algebraic classes are going to the algebraic classes. The Hodge classes anyway will go to the Hodge classes because it's a morphism of mixed Hodge structures, but we need to show this. And moreover, we need to show that this map is surjective. Okay, so we show that this map, when I restrict it to algebraic classes, this is surjective, specialization morphism. So then I can actually use the fact that I have an isomorphism here, and then I also need to show that I will be able, so this is for the Hodge, and this is for the alg. Okay, that I have an isomorphism here to conclude that I will have a isomorphism in the middle. Okay, so this is, I'm putting a lot of technical things under the rug, and I'm trying to just give you the basic philosophy of the proof. And I think I should stop here. Thank you.
Questions, comments?
I think the higher rank should also be possible. It would just be more, you know, there'll be more curves and more things that you'll have to take into account. Like, you know, when you're taking, as Professor Balaji was mentioning, this is kind of what curves you take, right? Here you have this, and here you have this, and this is kind of limited by the rank. And then you have to show more things, but I think the Gieseker moduli space exists for higher rank, and I think more or less this machinery can be done. So, yes.
So it's not easy to find in literature a proof for a general Jacobian. And there's a very good proof in the, I think, latest version of the book of Birkenhake and Lange.
Yeah, that's.
And by the way, it's should also remark, it's not necessary, but it's easier to prove for a general Abel variety.
Yes.
A general Jacobian, it's not easy to come by proofs. Everybody.
Yes. Thank you.
More questions or comments? If not, let's thank Inder again.